So there are a lot of implications to what we just talked about, in particular that matter has wave-like properties. Electrons have wave-like properties. Some atoms, smaller atoms, have wave-like properties that could be manipulated, and you can get diffraction patterns from them. And de Broglie, Louis de Broglie, a French scientist, had this idea that if light has a particle nature, then particles must have a wave nature. And he created an equation which is known as the de Broglie equation. It's often pronounced de Broglie. I will often say it that way until I learned not that long ago that it was de Broglie. But the de Broglie equation basically says this. Light has a momentum. This is the equation for momentum of light. And matter has momentum. Okay. And then he says, well, why don't we just set the two equal to each other? So let me explain to you what these things are. Now, H and lambda are the same terms we've been using the whole chapter. H is Planck's constant. Lambda is the wavelength of the light. But for matter, this is the mass of the particle, and this is its velocity. So momentum is what you feel when something runs into you, okay, or you run into something. Your mass times your velocity determines your momentum, and that creates that rebound that you feel when you hit and switch the direction of your momentum. You're feeling that change. P is the symbol we use for momentum. And I'm going to change the color because I think that's not going to show up that well. I hate writing in red all the time. So if you take just these two simple equations and you rearrange them, this is what you get. And this is known as de Broglie's equation. And it does this fundamental thing. It relates the mass and velocity of a particle to its wavelength. So why is it that we first observed, right, wave behavior in electrons? And the answer is pretty simply this. Electrons don't have much mass. So if you think about the mass of an electron being something like 9.11 times 10 to the minus 31 kilograms, everything else except subatomic particles that make up electrons, for example, everything else is heavier than an electron by far, by a factor of 2,000. And so that makes the matter wave of an electron more visible and more tangible for the experiments that we do. But like I said, they've done this now with atoms and have shown matter waves lengths for atoms. The other factor in this is velocity. So the combination of velocity and mass of the object, in this case the electron, lend itself for the electron's wave to be observed. Okay, so but for regular objects like a baseball or anything that you could tangibly hold or see, the mass is so much bigger than the mass of an electron. The matter waves are not visible. But where matter waves make a difference is when we're talking about electrons and atoms and the quantum nature of the electron in an atom. There's another important result that comes from the two-slit experiment for the electrons. So I'll go back to that slide just very briefly. So here's the double slit experiment for the electron, and at one point the electron behaves as a particle. It travels through space as a wave, and then gets detected at the screen as a particle. Now, when we try to detect where the electron is going through in terms of which slit it's going through, no matter what we do, if we detect the electron, it behaves as a particle. And as it behaves as a particle, then what happens is you lose the diffraction pattern that appears over here, and you get two lumps. So regardless of which slit the electron goes through, if you try to detect the electron at this slit, it behaves as a particle and ends up over here producing only two piles of electrons on the detector. So the fact that an electron can only be a wave or a particle is referred to as complementary properties. Now we think of like, oh, it's a compliment, like I tell you look good today, right? But this actually is different. Like one, you could either be one state or the other state. So they complement each other in the sense that you could be one or the other. So particle nature and wave nature of an electron are said to be complementary to each other. So a guy named Werner Heisenberg summarized this in a different way in something called the Heisenberg uncertainty principle. The big picture overlook of the uncertainty principle is basically this: because matter has wave properties, you can't know its position or its momentum exactly. You can't know its position, and momentum is the quantity in physics that we use to ascribe direction. We give direction to an object. It's why an object that's moving in one direction continues to move in another direction. So the uncertainty principle basically says then you can't know where exactly it is, and you can't know where exactly it's going. Okay, so you can't know exactly where, and I'm going to say an electron. This was developed for the electron, but it's true for everything. You can't know exactly where an electron is located or where it is going. You can't, and that's the momentum part of it. So in order to understand Heisenberg's equation, we have to sort of understand what it means when we say something has uncertainty in position. Okay, so this is delta x. This is said to be the uncertainty of position. Now we know that x means position usually, like this is where you would find it. So let's say an object is here. And I'm going to do a number line. It's a particle moving along a number line like this. Okay, and then if this is where the particle is, if an electron is a wave, there's only, you can't know exactly its position. This would be exact position. You can only know a window of position, like approximately where it is. And so the electron is actually fuzzy in this region that we indicate by the arrow. It's actually a fuzzy dot in this region. Okay, and I can't really even say dot. And so you might ask yourself, why is that? It's because if an electron is a wave, what does a wave look like? Well, waves go like this, right? There's squiggles that go on forever. And so you can only guess where the electron is in this position. And this value, this delta x, the delta x is this range here. The other thing that you can't know is you can't exactly know its momentum, its direction, or where it's going. So exactly which way this arrow is pointing is not exactly known. And so there's uncertainty in its trajectory, where we're expecting to find it. So that's why in the double slit experiment, we ended up sometimes the electron showing up here and sometimes the electron showing up down here, is because as it passes through one of these slits, again, we don't know which slit it goes through as a particle, and shows up as a particle over here, right? That's due to its uncertainty in momentum. We don't exactly, even though these particles are all traveling roughly in the same direction, we don't know exactly where these particles will end up. And that, again, is part of what is summarized by the uncertainty in its momentum, its trajectory going through the slits. Okay, so delta x is a range and delta v is a range. And it turns out when you take the product of these two things, they actually have to be greater than 4h over 4 pi. So this is a constant value. And in a sense, then, neither one of these values could be 0 because this is a non-zero value over here. The other thing this causes to happen is that at the limit, like let's say you did a perfect experiment, like you do that perfect titration or you do the perfect mass measurement, right? Really what the uncertainty principle would say in that instance is, in terms of behavior of this equation, well, if you get this really well, there's something else you don't know really well. That is, in other words, if you can get delta x, if you make that measurement delta x really small and you know as well as you can know where that electron is, then what happens is you have very little idea about the energy or the momentum of that electron. Because if this goes down, because this is a constant, this has to go up. So in the limit of a very good experiment, you do your best experiment ever, there's always going to be some uncertainty in one variable or the other. If you knew its momentum really well, then you wouldn't know its position very well. Again, this part of the complementary nature of an electron. It can't be both a particle, right, having an exact position, or a wave at the same time. So we'll end this section with looking at a couple of calculations. One will be calculating the matter wavelength for an electron traveling 15% the speed of light. And so the equation is lambda is equal to h over mv. So we need to find its velocity. So the speed of light is 3.0 times 10 to the 8th meters per second. So I need 15% of that, so that's 15 over 100. And that comes out to be 4.5 times 10 to the 7th. That's meters per second. H is still 6.626 times 10 to the minus 34 joule seconds. And then mass is 9.11 times 10 to the minus 31 kilograms. So now we can calculate the wavelength. It's 6.626 times 10 to the minus 34 joules times seconds divided by 9.11 times 10 to the minus 31 kilograms. And then the velocity is 4.5 times 10 to the minus 7, or sorry, plus 7 meters per second. And your wavelength ends up coming out as 1.616 times 10 to the minus 11 meters. Okay. Now, that's its uncertainty. That's its de Broglie wavelength in picometers. Now, this is in meters. We need to convert it over, and we know that. Oops. All right. A meter, right, and a picometer are related by 10 to the minus 12, and so that'll become 16.2. Actually, it's just to be 16 with 2 sig figs picometers, like that. I want to show you one other thing, because people often forget they can do this. When you see this number in scientific notation, if you recognize that 10 to the minus 12th is pico, then all you have to do is move this decimal over 1, so it becomes 16.16 times 10 to the minus 12. So if you move it to the right, you decrease the exponent, so I went more negative. And then you can just replace this with p. Okay. So there's this quantum cop, and he pulls this guy over, and he goes, "Do you have any idea how fast you were going back there?" And the guy says, "No." And quantum cop says, "Crap, me neither," right? Because if they are particles, right, there's an uncertainty in velocity. So what we're going to do in this problem is calculate the uncertainty in velocity of a an electron whose uncertainty is restricted to the diameter of a hydrogen atom. So thinking about what is the uncertainty in velocity if I know that there's an electron in an atom. So the equation, again, is delta x times m delta v has to be greater than or equal to h over 4 pi. Now h over 4 pi is a constant. It has a value of 5.27, and I just calculated it, times 10 to the minus 35 joules times second. So that's already a really small number, right? And now what we'll do is we'll end up dividing by the uncertainty in position and the mass of an electron. So ultimately what I'm doing is I'm calculating this, and it's going to have to be greater than 5.27 times 10 to the minus 35th joules times seconds. And then I'm dividing through by delta x and m. So we're going to say 120 picometers. And this is what I'm going to do. I'm going to say times 10 to the minus 12 meters. I'm just going to substitute like I did in that last problem. You can do straight substitution of the prefix if you can do it. And then the mass of the electron is still 9.11 times 10 to the minus 31 kilograms. I'll just say, like when I do these problems, most people don't calculate this ahead of time. I just find it's a lot easier to deal with this than to deal with this when I'm rearranging equations. So sometimes I'll go ahead and calculate bits and pieces just to make my life easier. Okay, so if I plug all that into a calculator, I get this, that delta V has to be greater than or equal to 4.8 times 10 to the 5th meters per second. So that's approximately 480,000 meters per second. That's its uncertainty in its velocity. So this is why the quantum cop is saying to this particle, like, do you have any idea how fast you were going back there? And neither one of them knows, because this is how uncertain the velocity of a particle in those dimensions is.